Hello all. I hope that you can hear me. So, uh, for today, we have a wonderful panel. So, we will be talking about the quantum risk analysis and quantum algorithms for macroeconomic modeling. I'm David Morquende. I'm the network manager at QuIC, and I can welcome you now to the episode 8 of QWave. So, for today, we'll have this panel, but first, let me talk a little bit about QuIC, as we always do in this series. For those people who may be joining for just looking at what quantum is giving us, or for this panel, or for because of they are interested about the quantum applied to finance, or just because this video appear on your YouTube feed. So for you who may be new, we are Europe's largest quantum industry association. We now have over 200 members across the quantum value chain in the different verticals of computing and simulations, communications, sensing and methodology, and enabled tech. We have startups, big corporates, universities, national labs, investors, and other stakeholders. And also, our mission is to grow and strengthen the quantum technology industry and position Europe as a global leader of the sector. Talking about hubs and communities, I want to introduce you also to QVC Summit. It's one of our events, like QExpo that I was explaining in the other episodes of QWave. But QVC Summit has another view. So we want to showcase what are we doing with our members, and it's a close event, members only and affiliates. So back in 2024, the summit took place in Italy, and we gathered more than 100 organizations in panels, workshops, networking, with many things. This year it's going to be in Geneva on November 26 and 27. And if you want to know more, please reach out to QuIC or to me, or let's talk. But now let's move to today's session. So let me get our speakers here. So for today, we have two wonderful speakers. First, Lucas Euler, that is a mathematician and quantum application scientist at Jos Quantum. During his master's at TU Darmstadt, he was primarily interested in logic and geometry. And with that, he provides a unique perspective on quantum information and helps the company to find innovative solutions. So hello, Lucas. Also, we have Niklas, who is a physicist and co-founder and managing director of Jos Quantum. So we have the big box here, and advises financial institutions and security companies in the field of quantum technologies. So also, hello, Niklas. It's a pleasure to have you here.
Hi.
As always, feel free to ask your questions in the chat, and we will address them during the Q&A session at the end. So for this wonderful panel, Lucas, the floor is yours. So if you can share your screen.
Mm-hmm. All right. So thank you, David, for the introduction. I hope you can see everything. If not, shout out.
Yeah.
So I will be talking about some of the applications that we've investigated over time. We are a small quantum software startup from Frankfurt. And primarily we look into applications of quantum computing and how they, how our clients could benefit from them and how that would look specifically. We then make proofs of concept and even implementations for them that they can eventually scale up. This is our like our groundwork, and we support research projects as well, and have also over time gained a lot of expertise in various areas, including also quantum communication and security topics. Here you see some of our partners that we've worked with over the years, and a picture of our team. We have 2 offices, one in Frankfurt, one in Berlin, and have like very diverse scientific backgrounds. So this is how we usually work. Somebody will come to us, and you will see some examples of this today, and have a problem that they want to solve, which is hard to solve for a classical computer. And they ask us, okay, can quantum computers help? How would that look? So we try to answer that question. And our policy is really always being very honest, because as most of you probably know, the answer is not always that obvious, and it's not always obviously yes. Like quantum computing doesn't always make everything better, and also not easily. So this is what we do. But usually you can find something or some aspect of the problem that can be handled with quantum computing. Then we implement that and even do a proof of concept on the machine. And you will see 2 examples of this today. Before we get into it, I want to quickly tease though our current effort, which is in order to enable these kind of things, quantum computing for companies and for research, we are now building our own paradigm for constructing quantum algorithms, which we call JQM. This is a new language for, just like QuIC, for example, for writing quantum circuits. It is, of course, based in Germany, as we are, and it's also made to be very lightweight, and it doesn't like have a lot of dependencies, and not a lot of unnecessary sugar in it, basically, to which just makes the package larger. It is really what you need to develop, and not too much more than that. But on top of this minimalistic core, we built also an application where you can construct these kind of algorithms using graphs, as you can see here on the bottom right. This is, of course, very complicated. We will be showcasing these things next week in the World of Quantum for the first time. So this is a exclusive teaser for you. And if you are there, please check it out. And you can construct these kind of hybrid workflows, even of classical and quantum things, as these intuitive graphs. And this is built on top of our language JQM. Okay, so now I will get into today's topics, which is quantum risk analysis, and then later we will see an example of macroeconomic modeling. So the risk analysis, what does that mean? It's actually not that hard to explain. So there is a lot of people, especially in the financial world, that are interested in modeling risks. So, and essentially the way the models often look is a probabilistic graph of nodes, which can trigger independently, but then also trigger each other. So here there's this super small model, which also is not backed up by any real data. This is something we came up with. Don't be scared. This is, here you see this political crisis node. It can just trigger by itself, and you estimate the probability to be 50%. And then if it does trigger, it can also have a chain reaction and trigger one of the other 2 nodes or both, depending on the probability of the edge. And many companies, like, for example, the Deutsche Börse Group, for which we developed this, is interested in these models. And of course, they have then pretty big graphs with complicated connections. And it's really hard to then figure out the dynamics of this. So the first step that we need to take is, and this is why this is such a fortunate example, encode this in a quantum circuit. So just encode the classical data in the quantum circuit. And this is actually very simple, or rather simple to do. here because you just need to rotate the qubits accordingly for their initial probability, the one that is inside the nodes. And then whenever you have such an edge, you just do a controlled rotation to increase the probability of the node that follows. And so this is a very efficient encoding of this relevant classical data into a quantum circuit. And this is not necessarily a given. Like, there's a lot of classical data, a lot of problems where that already kind of fail at the encoding step. So this is not one of those. This thing works. But then what can you do with this? So this is just the classical data encoded, doesn't give any advantage yet. The advantage comes from something called quantum amplitude estimation. Maybe you've heard of it before. Here in a nutshell, it lets you essentially ask a question about a probability amplitude. So you just ask, what is the probability of this specific combination of events occurring? And the only way to solve that classically is to do Monte Carlo simulation. So you just like run your model over and over and try to kind of estimate the probability. But this can get very difficult for when the models are large and complicated. And also it is not very reliable for combinations of events that are rare. But especially in the financial world, you might be interested in like these rare events that have huge impact on what you do. And like currently, classical computers, they reach a limit where they can't find out certain things that are really relevant for companies. So here, what's the answer? Quantum amplitude estimation. And the result of that would just look like this. So it is very, I mean, for one who hasn't like spent much time in the quantum information world, it's a very weird thing because you can ask the probability directly. So the result tells you here with 99% certainty, the probability of triggering your event here was about 15%. This is how amplitude estimation works. Instead of like in Monte Carlo simulation, getting the events that trigger, the quantum computer can ask directly for the probability, which is of course a bit strange, but that's how it works. And here's how the quantum circuit for that looks. I mean, at the top you just see a little code snippet. I just wanted to show this because this is the kind of thing we implement that then the end user or like our client really just has to put in like the minimal amount of inputs, and then our function handles all the things and builds you a circuit. And on the bottom, you see the circuit for quantum amplitude estimation, which there's not enough time to explain in the greatest detail, but essentially you build these G's here at the bottom. These are called Grover operators, and they encode something like they mark events in the model, like if they happen or not. And then you do these things called phase kickbacks, which is like here via these controlled operations, and then you do a quantum Fourier transform to turn that into a bit encoding. So like this is for those who know what I mean here. This is just a quick explanation. And this alone gives you a quadratic speedup over doing it classically. But the really business relevant case is, and this is where the classical computers reach their limits, is something called sensitivity analysis. So when you have such a big model, it is based, of course, still on estimates. So like I showed earlier with this political crisis, there was this estimate of 50%. And you might want to know, what if I was wrong? Like, what if my estimates are slightly off? So, and this is what sensitivity analysis does. You ask, how sensitive is the overall dynamics of my model to these one or two parameters here that I'm not really so sure about. So this is something that is really hard to do classically, because it's not enough to just do like one Monte Carlo simulation. You have to kind of like just try for different parameters essentially. We can also do this much better with a classical computer, with a quantum computer. Sorry. And the way we do this is we add to the risk model this cost factor. This is very easy encoding, as you see here. And then we perform actually a Grover search. So I mean, many of you know the Grover search algorithm, and of course, it's always gets a bit of a bad rap because it's one of those situations where usually it's hard to encode the classical data such that you can perform a Grover search. But here we have it encoded as already the quantum amplitude estimation. Because now what we are doing is we are searching, we are saying, please look at this and this parameter, and then we are searching for configurations that make the model basically explode. That's how you can think of it. So we do Grover search to find configurations of parameters that are bad, that we don't really want to see. And then if we don't find any, we can be happy, like, okay, it's okay if we didn't make mistakes in our estimates. If we find some configurations, then that's really relevant for the company to be aware of this kind of risk. And we predict that, for example, with the models that Deutsche Börse is using, like with the size of the models that they are using, this will be practically relevant, like actually give them a business advantage when there is around 200 error-corrected qubits. So we think that this will be one of the first applications that will be relevant in the financial sector. And because we genuinely believe that, we have invested quite a lot of time into understanding how to do this kind of thing and how to make it better. And for example, one of the tricks we came up with is parallelizing the amplitude estimations itself. So maybe earlier you remember that you saw all of these Grover operators G, and they happened one after the other. These Grover operators are pretty big. They are like the biggest, it's unassuming in this picture, but they are the biggest part of the circuit. So what you can do is by kind of rearranging the amplitude estimation, you can make it so that they are executed all at the same time. And this reduces the depth of the circuit by a lot. And you can do more things on top of that, like flagging errors using this parallelized architecture and so on. So basically, we understand quite well how to do this sensitivity analysis and amplitude estimation for these risk models. Yeah. So this was this use case number one that we wanted to talk about, which we think is very near term. Now I want to also go to another use case, which is even more powerful, but also further in the future. So this is solving matrix equations, which can be used in particular for macroeconomic simulations. So this is something that we looked at together with Deutsche Bundesbank, the central bank of Germany, and they are interested in, of course, simulating the the macroeconomy, like the economy of a country or even international economy. And this is, of course, a complicated system, like a complicated dynamical system. You don't need to understand all the details here. What's important for you is at the core of this simulation, they are called perfect foresight simulation, is the solution of a matrix equation for a pretty big matrix, like that has that's very high dimensional. So, but the matrix has a lot of structure that you can see here. There's this somewhat repetitive block form, and everything outside of those blocks are zero. And even the blocks themselves, they look like what you see here on the right. They are very sparse, so they don't have a lot of entries. But why am I telling you this? This is again one of those situations where the classical data that we are looking at has a lot of structure and also the sparsity, so it's not very dense. And this is a very important requirement for encoding this into a quantum computer again. So in the situation of these macroeconomic simulations, you have these like highly structured matrices which don't have too many entries on them that you need to look at. So this makes you even enables you to use a quantum computer. Like if it turned out that this matrix equation was super full and chaotic, you could just forget about using a quantum computer. This is what I meant earlier with us being honest about like problems, because not everything can be solved in this way. But this situation again is promising for quantum computing, and here's how it works mathematically. So this is also more for completeness. Don't worry if you don't get it in this 2 minutes that I have here to explain. But how it works, and it's quite interesting actually, this HHL algorithm was developed by Harrow, Hassidim, and Lloyd, is you encode the matrix, and the matrix itself doesn't have to be unitary, but you can encode it then in a unitary matrix via Hamiltonian simulation. This is what you see here. And then this matrix U that you get out of the Hamiltonian simulation, it has the eigenvalues of A as its eigenfaces. So even though it's a different matrix than A, the eigenvalues of A are still encoded into it. And then we can do phase estimation. So this is similar to the amplitude estimation that I already showed you earlier, as one of the steps of this algorithm, to get them out and read those eigenvalues. And then we can just apply the inverse and stitch everything back together. So in a nutshell, you encode the matrix, you take it apart in the quantum computer, and then you apply all of the inversions, and then you stitch it back together. This is what you can see here. This is how the circuit vaguely looks. Of course, in all of these blocks, there's a lot of stuff, but there is one particular step, and here it's only one step of the algorithm, is this phase estimation. And then in the end, you reverse the phase estimation. This is the stitching back together. And yeah, this algorithm is very powerful. So it is kind of on par with, in terms of complexity, with the famous Shor algorithm. But as you probably know, Shor, using the Shor algorithm is quite demanding for a quantum computer. So it's a bit far away in the future. And what happens is that actually HHL doesn't even use that many qubits necessarily, or like in theory, because the encoding is quite, this Hamiltonian simulation encoding can be quite efficient. So maybe around 20 to 30 qubits would theoretically be enough. But one layer of error correction isn't going to do it here, because we are talking like millions of operations that need to be performed without error in order for this algorithm to properly work for a big example. This is different from the risk models that I talked about, where we are more talking thousands of operations. That would already be enough. But here for HHL, we need millions. So this is on another level. And here are some roadmaps of hardware companies, which are, of course, predicting the first logical qubits and or like usable, like enough, the first relevant number of logical qubits, let me say that, around like maybe 2030 or so. And so there's a long way to go still for HHL then to be executed. In particular, here's the company AQT from Austria, Alpine Quantum Technologies, which is a regular partner of us, and we want to shout them out here, especially because they helped us test this HHL algorithm for a super small matrix. So this the example that you see here is a 2x2 matrix. But we tested it on their machine. So we know actually that this algorithm works already, which is cool because HHL, like I said, is super difficult. But for a small example, you can already show on a real quantum computer that it works. And yeah, AQT has really been a great partner for these kind of things. We also tested the risk models that I talked about earlier on their machines a few years ago. And yeah, with that, I am finished actually with my talk. I'm more on time than I thought I would be even. And if you have any questions, I think type them in the chat and we can go to the Q&A. And here is again maybe our slide for JQM, which you might be interested in to look at in World of Quantum.
Thank you so much, Lucas. So it has been great. Let me get to the Q&A slide. First of all, I'm so pleased about what I'm seeing and to like understand and fully see the things that you are doing. Also with this programming language that you have just shown. So I'm very keen to see that live and to being able to test it. Also, I know that our audience is usually quite shy in the chat, but please use the chat to ask questions. I know that after the equation that Lucas was showing, it is usually hard to follow because you go to your computer and try to replicate everything because I know you are keen to do so. But for the first question that I have here, that actually the first question was about the different roadmaps. I was writing like preparing my question for you, but you actually show the different roadmaps for different companies, and that's so. It's not my first question. My first question actually is like you're saying that we need to scale up, and you show this huge matrix, like potential matrix that we'll have to solve in order to simulate actually the thing. How big do we have to scale up in order to have something usable? Because you were saying, yeah, with like around 20 or 30 qubits, we can maybe start to doing things, but we know that that's not true because also you said the error correction that is needed. So how big do we have to scale up?
I mean, so I think the best way to answer that is, I mean, like I said, it's the number of operations that need to be performed without error. So for the risk models, this one level of error correction is enough because you only need around like hundreds to thousands of operations. But yeah, we need millions of operations to be performed, and I mean for that we need several layers of error correction. We expect that this will take at least another 5 to 10 more years. Of course, it's always hard to say what kind of innovations might be around the corner, but this is not one of the first use cases. Yeah.
Okay. And also, I want to know Niklas' perspective, like from the management perspective, like you are ruling, you're a co-founder of the company. Um, do you see that timeline or time scale working with other companies and within your company something feasible? Like 10 to 10 years is something that you are comfortable to say or to do?
You mean about the specific use cases, or
Well, in general, on the all use cases that you have, and also in specific on the one that we have just seen.
yeah, okay. Well, so that's basically the job we are doing since now 7 years. We're working very close with the hardware companies, so on any fundamental technology. So started with working a lot with IBM, so superconducting, ion trap companies, neutral atoms, NV centers, photonics, to exactly do this, like map basically the hardware roadmaps to the what we think relevant use cases from top. So it's about understanding exactly how the hardware works, how parts of like how the compilation works, what kind of error correction can be introduced, what's the state of technology today and over the next like 2 to 3 years that are possible to forecast, and then like look from the algorithm, like use case level, so mathematical modeling level, going down to the algorithm level, looking into like potential more efficient implementations or architectures. Like one example Lucas just showed is internally called phaser, which is this parallel phase estimation and coding. And that's actually like it's like a dance, like from top and from the bottom, to see how can we do things more efficient from the hardware side, from the algorithm side. So I mean, it's always hard to predict stuff. We are searching for the tiny models that we think provides enough benefit but runs very early stage. And this is like these risk models. I mean, we are talking here about so the use case Lucas showed is about business risk. So if you look at the risk a bank, for example, a financial institution needs to calculate to come up with their it's called risk-weighted assets. in their balance sheet, then they need to do it on different like kind of risk models, risk types. So it's credit risk, so counterparty risk, it's market risk, it's operational risk, and then valuation adjustments basically. And in the operational risk, you find parts of it as business risk. So basically, what kind of macroeconomic impact my company can have due to some external events, can be technological events, can be political events, wars, pandemics. I mean, we've seen a lot in the last in the last 7 years.
Yeah.
So I mean, this specific use case may not have the really like huge impact in the first place, but has the chance to show like that the technology is actually working and applied in industry, and that's not too far out. I mean, in terms of the risk models, we don't need a lot of qubits.
Yeah.
We don't need these huge circuits like in HHL. So these two use cases give two different kind of perspectives. One,
Yeah.
like HHL is like, I mean, that's the big thing we are after. Like that would be quantum AI, basically matrix operations. And the other one is risk circuits, which is maybe a little bit niche and might not disrupt like a huge field in the beginning, but has the potential to run like within the next few years.
Yeah, I love the approach. That if I were you, I will do the same that you're doing because it's really wise. Go from like top to down, like from the software to the hardware, and down like from the bottom to the top, like looking at the different hardware providers and how they're doing so. Coming back to the risk analysis, you were talking about this specific use case and risk analysis and the learnings that you have. So actually, what are the most important learnings that you have so far in applying quantum to risk analysis? Like any things that really showcase, any advice to the our audience?
Yeah, well, maybe I'll answer first because what was actually in the field of optimization, where we also had many, like several research projects in the beginning, the biggest learning was what is actually my classical benchmark? Like, what is the state of the art of algorithms that I actually have and can apply to my problem? Because like in the early stage, like in 2018, 19, people talking about portfolio optimization and stuff like this, where some part of the problem seems to be like very suitable for a quantum because of the quadratic form of the covariance matrix and stuff like this. But at the end, I mean, you see that the encoding blows up and the the classical benchmarks are really good and really fast. So in the field of mixed integer programming, for example, which is a kind of combinatorial optimization, I mean, classical solvers, they are very strong, and you are then in the field of comparing a heuristic versus another heuristic, which is very, very use case specific. And you can tweak it a little bit here, a little bit there, and make it like one magnitude better to a specific problem formulation, like for a specific mathematical problem. So that was a big learning to see actually and benchmark quantum against current classical solutions, because I mean the classical computing side is not sleeping. I mean, with currently people working on GPUs and making them like not only from hardware but also like from the software integration better, and the integration and orchestration part between CPUs, GPUs, and special purpose devices like TPUs or others. I mean, quantum is in a competition with these kind of computing architectures, like at least the quantum computation part. So you always need to know your benchmark. Long story short.
Lucas, anything to add? Or?
I mean, I think I agree with all of these points, and what I could add is that I think it's interesting that it's not always necessarily obvious if a problem can be formulated in this way, that like for example these risk models, because there's this big discrepancy between, you know, the client has a problem formulation that is very high level, and then we need to kind of do it on a quantum computer where you are programming it almost in like machine code. So you can actually sometimes find these kind of interesting models in unexpected places. That's I think that's something interesting as well.
Okay. Talking also about optimization and the GPUs and this realm, a question that I really have, and I believe most of people has, is what application areas do you see emerging right now in the intersection of quantum and AI? We are talking a little bit about the CPUs and AI and optimization and quantum. So mostly quantum for AI, but if you want to add something for AI to quantum, it would be great.
So, I mean, for example, Niklas teased this a bit. This HHR algorithm is, of course, relevant for AI or for machine learning, because there you have huge matrix equations that you need to solve. But this is, yeah, very far in the future. I mean, otherwise, we are also have looked into various approaches like quantum machine learning, which is different from, you know, encoding just the matrix into a quantum circuit and trying to solve it, but actually doing the optimization directly or like the parameter search directly on the in a quantum circuit with parameters. And yeah, there's many promising avenues like that. There's always a bit of uncertainty, of course. Like there's no obvious thing where quantum computing can already speed up AI or something like that, or quantum machine learning has like a huge advantage. The best is always if you have a problem that already is a quantum problem. For example, we have a paper about using quantum machine learning for quantum key distribution or like problems related to that. So if you're already in that realm, it's very these ideas from machine learning are very useful.
Okay. We are talking about QQD. Security comes to my mind, and also the encoding that you were talking at the very beginning is the data. So for you, or I don't know if you have this problem, or if you are looking into that, about the regulation on the data, on the financial products, forecastings. How do you see the like the policies or problems around quantum algorithms applied to this, or if it's the same problem or the same disadvantage that you have with classical data, or the quantum algorithms works in a specific way that we'll have to be aware?
Yeah. So talking about regulation, maybe one thing about regulation and risk management. I mean, financial sector is highly regulated. So there are possibilities to use like a company's own risk models for credit risk or market risk, for example, like internal risk. But you are always under the review of supervisors. So if you can like come up with a new approach, the supervisors and regulators need to understand, and you need to be compliant under like certain formulations, like and in financial risk there are quite many. So MA risk or Basel, they actually, the supervisors tell you how the risk models or the structure should look like and how they can audit them. And well, you cannot just come up with a new model, and especially not with such a new technique. I mean, it's fundamentally different if you go from a like a deterministic model to like a probabilistic model like we have in quantum. So that's a pretty tough question for regulators, but regulators are actually already looking in this technology. So for example, ECB and our partners from Bundesbank, they are looking into quantum already. learn and like see how the market may adapt in the future. Well, and there is the big topic about AI regulation and what data to use. I think that's I mean, for quantum, it's the same impact and topic as for a classical model. I think there is no big difference.
But that's good that the regulator are already looking onto this. It's a new field, and we have to be prepared. Just one last question from my side, and we can go for the chat questions. So from my side, the last question is, what talent profiles or skills do you feel that are needed to overcome this realm?
Yeah. So, Lucas, maybe I'll answer this, but you can go afterwards and tell me your perspective about this. But what we saw at Jos Quantum at the beginning, because like we were in the beginning 3 physicists. So I'm having an experimental physicist background. Marcus, my co-founder, is coming from theoretical physics. And our 2 others are also, well, Sven is from theoretical physics as well. Thomas has like more than 20 years of experience in quantum information science. So 3 physicists, 1 computer scientist. And this was like really crucial that you get together like skills from different fields that are relevant in quantum. Like first, okay, talk to a physicist about quantum, but you need somebody who really understands like the information side and the classical information side as well. So, okay, there we had like 1 person knowing the classical and the quantum information side, but having somebody like Lucas, for example, in the team who has like the perspective from mathematics and logic, that's really valuable. And well, we're having people from different backgrounds, so from engineering, software, and so basically it's the combination of computer science, physics, mathematics, and computer science or software engineering, and especially also machine learning. And that's basically the whole team at Jos Quantum currently.
Lucas, do you want to add something?
Yeah, I think I agree with that. And on top of that, I would add what's important is that people are able to, well, communicate between those fields, but also communicate what, like their knowledge, sorry, to clients. So all of this like highly theoretical knowledge that we have is sometimes a bit overwhelming, especially if you talk to somebody about quantum computing for the first time. They can easily get overwhelmed. So I think this is a very important skill to develop, this talking to people and getting them on board with quantum computing and not having them run away. Basically.
Yeah, I completely agree. I'm not a physicist, and I have seen several of my partners or other people around the technology itself that is needed actually to overcome this new quantum world. So I'm so happy to hear that. Well, let's go for the questions from the audience. So the first question that we have is from Jan. So how far you get with the client? Is it in use in any manner?
Yeah, that's a good question. I mean, so of course, quantum computing is not on the level that it provides actual advantage in this moment. Like nobody ever in the world has, like no company is actually using quantum computers for a real advantage. But so the work's often very explorative. But I do know that like some clients, they keep the code that we wrote for them, and it is ready to be used when the hardware is on the level that is needed for their problem. So I mean, nobody ever is using like quantum computers for advantage right now, but the code, like what we provide, is actually usable for it.
Yeah, so the quantum readiness that we are talking in many industries, not only to like apply the actual software, also to be aware that how should we integrate this into like a stream. I'm talking in general in the industry, not specifically here. Niklas, did you want to say something?
Yeah, and to add something, the process how to how to find and explore relevant applications and really go down from the level of an application to what needs to be done and where do I really need to look at specific technological advances. That's like the process and the providing this kind of skill set and building up a team at a client side. Doesn't have to be like 50 people, but 1 or 2 people really looking down to and understanding what's at the bottom and what are my strategic implications for that. I think this is like really relevant about the process and how to encounter.
Yeah. A really tight question actually from Samuel is how do your customers react to the timeline projections, especially when they are long like for the HHL algorithm?
Yeah, also a good question. Kind of ties into the one from before.
Yeah.
So, like, of course, it's a bit of a bummer if you're like excited to do quantum computing and then we give the honest answer. It will be a few more years until you can do this specific thing. But I also have to say, like, my feeling is that a lot of the clients are just relieved to be getting the honest information because like on the news they saw some things about quantum computing this, quantum computing that, new chip has been developed or something, and they think like they're super behind and everything, and we just have to come up and like and kind of clean up this somewhat like maybe even misinformation that they have received about the state of the technology. So I think, of course, they would be more excited if they could just use the quantum computer right now. But I think they're also relieved, and it builds also trust to like long-term trust to those people. I think that's what I would say.
Yeah, and you can think maybe about we're trying to give a client the right pace, the right velocity. So sometimes like people feel they are really missing out stuff because hype and FOMO created. So people run and invest a lot of money, and after half a year or a year, the dilution comes, and that's not necessary. But doing nothing is also wrong. So you need to have the right
right partners, to go with.
the
Totally
right
agree.
velocity, exactly.
Yeah. Also, and this is a question that somehow I already asked, but just before the streaming. So GQM is written mostly in Python or parts are in Rust or something else?
So this is something that, I mean, you of course will see when it's released, and parts of it will also be in open source. It is mostly, I would say, Python, so nothing is written in Rust of it. And it is vaguely dependent on Python, but really is made in such a way that it is independent of any like big libraries or something like that. So the way it is set up is very minimalistic. It is kind of embedded in Python, but even that is not necessarily a huge dependency.
Oh, that's great. And it's also great that part of it will be open source. I love that.
Exactly. And with part of it, we mean like we have basically it's about, Lucas showed the slide. It's about like 3 layers of software basically. And the core basis, this is what we are planning to release open source. I mean, we are already using this software package for our own developments and integrations, and also for working on our own IP. And connecting to hardware vendors. So now we think is a good time to also release it to partners that they can connect and use it. And I mean, on top there is a kind of workflow, event-driven workflow management, and also Studio is an end-user low-code UI where you can connect workflows, classical nodes and quantum nodes to build, for example, quantum programs in not only for computing, but also for communication, quantum communication. So, and this is something which is, in our opinion, really relevant near term, because the big scale quantum computers, they need to have they need to be connected somehow, and that's where the communication part comes in.
Yeah, that's great, because the next question is actually really about the scaling up, but not really about the scaling up. So instead of scaling up the amount of qubits and improvement of error correction, what are the other requirements your use cases have towards quantum computers? Any other development that you require?
Okay, I mean, I suppose this is hardware requirements really that could come on top of it. I mean, I guess the error correction is more like the blanket term, like this is what we need. I wouldn't say there's something specific that I could say in terms of like connectivity or shuttling or something like this, if this is what you're asking. But a big thing that I think could be very useful is to have, first of all, maybe distributed quantum computing, and then also integration of quantum computing and classical computing. So basically the hardware, when it's there, it also needs to be ready to be used and like be able to be integrated into the workflows of the companies. I mean, this is something that needs to happen at some point, because like a lot of the machines that are out there, you can kind of use them, but then you have to go and talk to the hardware provider. You have to like say, okay, what kind of format do you need and stuff like that. Like this can't be the workflow for the end user. The end user has to be able to just do it and easily like send everything there, and then have like maybe even a loop of classical and quantum optimization, this kind of thing. So this addressing needs to be there. This is also something that we are trying to do with the software that we are building.
Yeah, right. Actually, is the thing that is blocking right now. And the last question, yeah, you can.
Maybe before we go to the next question, Lucas teasered a phasor, so the parallel version of the phase estimation that can be used for the for the amplitude estimation. This is actually an architecture. This is maybe going in the direction about like what developments do we require. Well, this kind of architecture gives you a very flexible architecture of quantum qubit registers. So we don't need this kind of like hexagonal form like IBM has, or like other topologies, connections, but like anything that, for example, in the in this architecture, we only require like fully connection in a central node, and all other like kickbacks can be in a separate qubit register where we only need a single connection between the registers. So it really depends on what the hardware is able about. But what I want to say is we can, with our approach, be very flexible in making things work.
That's right. That's what we said in a question that I asked about the top to bottom and bottom to top. That it's good to have both, like hardware things, but also being able to adapt to different hardwares. It's really good. Well, and the last question that is in the chat, and I guess it's going to be the last question for today from Samuel, is: do you think that the quadratic speedup is enough to provide some real practical value, or will it not be absorbed by operational overheads and error? Tough question, eh?
Yeah.
It's a good point, because of course, I mean, the holy grail always is this exponential speed up. That's what everybody always talks about. But I mean, quadratic to linear is already a significant difference. So I mean, we did a benchmark of this when we were talking to Deutsche Börse about the models that they would be interested in, and we figured out that the classical methods would take many years. I think it was around 13 years or so to get to the same precision that you can get to with the quantum computer in minutes. So of course, it's not exponential, but it is still significant. And I'm not sure what exactly you mean with the operational overheads here, because I mean, so the error correction in the quantum computer that that shouldn't like increase the runtime by so significantly that you would catch up with these 13 years. But operational overheads are actually in these risk models not so huge. In HHL, that's more of a problem with this big matrices, and you have to do a lot of classical preparations to do the encoding and stuff. For the risk models, there's pretty little classical overhead, actually. So that's not a big problem there. Yeah.
Great. So we have get to the end of this session. So let me first thanks Lucas and Niklas for the insights. I think that this has been a really good session today with a really good introduction to the topic and a really good discussion. So again, thanks for joining us. Thanks also to the people who joined to the live through YouTube. And a reminder that this session will be available in YouTube. So please share, like, comment, the usual typical things in YouTube that helps us a lot to grow. And also share to your colleagues. There will be someone who wants to see this and doesn't have don't have the link. Again, thank you and see you next time. Bye.
Thank you.